This is going to be 7.6 total differentials. So most of you guys will already have figured what differentials are, and if you didn't, well, it's fine. I will review a little bit of what differentials are, and they should seem very similar to things that we've done before in calculus. So let's start off with the differential. And you may have seen this in single variable calculus. So let me just write here, single variable. We defined a differential to be the following way. So the differential was basically dy is equal to f prime of x dx, okay, for some function, f of x. So this looks very similar to kind of like u substitution, where you have du equals the derivative of the function dx, which basically is the same thing. Okay, instead here we have dy. So this is what we call the differential. This is by definition the differential. So basically, a little change of y can be estimated with a derivative. That's basically what it's saying. So now, since we're in the multivariable calculus world, so now we have multivariables. Calculus. We are going to define the differential with now a function f of x comma y. So now we have two variables. What will the differential be in this case? Well, it's basically the same thing. Okay, we're going to have df is going to be equal to the partial derivative with respect to x of the function, and we're going to write dx plus the partial derivative with respect to y of the function times dy. Okay, so basically it's the same thing as this guy, but now because we have two variables, we're going to have f sub x with dx plus f sub y times dy. So this is going to be the differential. So here is basically the formula. Okay, so let's do a couple of examples to really be able to understand how the differential works. So here is my example. Find the differential. Okay, and I'm going to call it find the total differential. Okay, so let's start off with the first problem. Let's say for this one we want to figure out f sub x comma y is equal to x squared y plus y to the negative 2 plus e to the xy. Okay, so what would be the total differential in this case? So first things first, let's go ahead and write down the formula for the differential. We know that df is going to be equal to the partial derivative with respect to x dx plus the partial derivative with respect to y dy. Okay, so first we need to figure out two pieces of information, which is f sub x and f sub y. Okay, so first let's figure out what f sub x should be. So that's the partial derivative with respect to x. So let's take the partial derivative of this guy. That's going to be 2xy. Here, notice that there's no x, so this is going to go away. So that's 0. And then this guy, we're going to take the derivative of e to the xy, which is going to be plus e to the xy times the derivative of the inside using the chain rule, which is just going to be y. Okay, and then let's figure out the total differential. The derivative of f sub y. Okay, so now we're going to take the derivative of y. That's going to give us 1. We're left with an x squared. Here now, because this is y, let's go ahead and take the derivative of that. That's going to give us negative 2y to the negative 3. And then same thing with the other one is going to be plus e to the xy times x. Okay, so now all we have to do is basically plug these two pieces of information in here and in here. So my total differential will just be df is equal to the first function, which is going to be 2xy, which is this guy, 2xy plus, let me put the y in the front, e to the xy. And then we're going to write dx, because that's the next thing, plus the next part, which is going to be x squared minus 2y to the negative 3 plus x e to the xy. And then we're going to write dy. Okay? And that's basically all you're doing. You're just taking the partial derivatives of the original function and then plugging them into the formula. That's basically just it. And just writing dx and then just writing dy. Okay, let's do another problem. Okay, part B. So let's find the total differential of the following. So z is equal to ln of x squared plus y cubed. Okay, so what would be the total differential in this case? So we're going to first write out the formula. So the formula is going to be df, but notice that we don't have f in this case. We don't have this f. Instead, we have this z. So instead of df, it's going to be dz. It's going to be equal to the partial derivative, of z with respect to x dx plus the partial derivative of z sub y dy. Okay? So notice all I just really changed was the f to a z. That's basically all I did, but it's still the same formula. Okay, so let's figure out what the partial derivative with respect to x is going to be. So the derivative of natural log is going to be 1 over the inside, which is going to be x squared plus y cubed, times the derivative of the inside with respect to x, which is going to be 2x for x squared, and the derivative of y cubed, well, that's a constant, so it's going to be 0. So what I have is 2x over x squared plus y cubed. Okay, then I'm going to take the partial derivative with respect to y. Okay, same thing. That's going to be 1 over the inside, x squared plus y cubed, times the derivative of the inside with respect to y. X squared is a constant, so that goes away. The derivative of y cubed is going to be 3y squared. And that gives me 3y squared over x squared plus y cubed. Okay? So now all I have to do is plug these guys back into the formula. Okay, so I'm going to have dz is equal to, the first partial derivative with respect to x is 2x over x squared plus y cubed. I'm going to write dx plus the partial derivative with respect to y. Okay, it's going to be 3y squared over x squared plus y cubed dy. Okay, and that's my answer for that part. Okay, all right, so you might be wondering, okay, so what is the whole point of all of this? Okay, why do I need to be doing all these differentials? Well, it'll make sense a little bit when we get to integration, but for now, you can kind of think about it this way. So one of the ways that we are able to apply this is that we can try to figure out that the change of f can be approximated with the differential. Okay, so if I wanted to change f by a particular amount, okay, and I wanted to figure out how much did it change, I can just use this derivative as to approximate it. So you can kind of think about it this way, that delta f, the change in f, is just equal to f of x plus a little change in x, and then y plus a little change in y. So basically, if I change x and y with a little bit, by a little bit amount, and I subtract it by the original, that's going to give me basically the change in f. How much is f changing? Okay, and we know that differential df is equal to f sub x dx plus f sub y dy. So you can kind of see that in terms of mathematically speaking, it might be easier to just deal with a derivative than it might be to plug in new information into the original function. Okay, so that's basically what the differential is used for. So it's helpful to figure out errors and changes by just using the derivative. So in the next video, I'm going to show you guys a problem on which you use the differential and comparing it with the actual function.